All right, so let's have a look at the timers and counters, the rest of it, mode 2 and stuff. So actually, I had recorded it, but then I realized that the microphone wasn't on, so I'm re-recording it. So, anyways, so the mode 2 essentially is called the auto reload mode. And the reason for that is because, so imagine this is your timer. You can imagine this to be your timer 0. And your timer essentially has TL and TH, each is going to be 8 bits wide. So, in your 8051's mode 2, you use only TL0 in a physical sense, but you do not put any value into the timer itself. So how it works is you suppose you want some time delay, you calculate the time delay you want, and then you load up that value in the TH register. And then what TL will have nothing in it. So what 8051 does is it automatically loads the value which you put in TL into TH, and then it starts incrementing from there till it rolls over to 0. That's how the mode 2 works. So yeah, suppose TH0 holds a value FD and TL0 value holds the value FE. After every 2 cycles, TL0 resets the value stored in to the value stored in TH0, which means this happens, then this value comes there, and then it does that. So you use this very much in serial communication. You'll have a look. You'll have a look at it there. So let's just look at some codes. So it works in the same way. You start off normally by defining your T mod, but here you don't define your TL0. You just directly put the TH value, and then that value automatically gets loaded in. You clear the timer flag, you start it, and yeah, it just works like your standard timer does. Uh, there's another mode which you won't really get too many questions from. It's called the mode 3, which is the split timer mode. So how this works exactly is your timer itself is split, and it works as two separate 8-bit timers. So your TH and TL work independently of each other as two separate timers. And why do you do this? So that suppose you want to do serial communication for which you need to use one timer, and you also want to do some, pulse wave generation stuff. So in that case, you can use this. Suppose I want two sets of pulses. I can use TH0 for one of them, I can use TL0 for the other, and I can use my timer 1 for my serial communication. That's why it was developed. So how this works is there is like one thing which you need to keep in mind for this is that uh, the 16-bit timer 1 or like timer 0, whichever timer you use, it can be configured to operate in any mode. So each of those individual timers, right, you can change them and make them work in whatever fashion you want to, but you cannot disable it because there's no control bit to do so. So basically, for instance, you will be able to, your timer, suppose TH0 and TL0, they're individually working as two separate timers, 8 bits. The reason there is no, and suppose your timer 1 is being used for whatever. The reason you won't have any control bit is because you will define TL0 as TR0 and you'll define TH0 as TR1. That's what's written here. All the control bits of 16-bit timer 1 now control the 8-bit timer 1. If they've taken the example of timer 1 instead of timer 0, but yeah. So yeah, the operation will be restricted when it comes to this. And yeah, like I said earlier, you may not stop the real timer 1 since the bits that are used to start the real timer 1 are now linked to TH0. Let me just sum it up real quick because I feel like it's getting a bit confusing. Basically, this is one timer, and this is one timer, TH0, TL0, timer 2, 8 bits, 8 bits, 16 bits, works independently, works independently, works independently, defined as TR0, defined as TR1. Since this is defined as TR1, you cannot use any of the control bits of this timer. Sorry, this will be timer 1, this is timer 0. You cannot use any control bits of timer 1 to actually control this. That's it. That's essentially all you need to know. You won't really have any questions of this, so you don't have to worry much. But in case you do, you know how it works. We look at some examples if there are any, and we can move on. So let's look at this question. Square wave of 50% duty cycle. What does 50% duty cycle mean? On and off times need to be equal. What does 25% duty cycle mean? It's on for 25%, off for 75% of the time. So equal portions on port 1.5 bit. What does that mean? You will configure P1.5 as your output port. Output port O for 0. So you will clear P1.5. Timer 0 is used to generate the time delay, analyze the program. Let's have a look at this program. First of all, before you begin anything, you have to tell Tmod. Think of it in a systematic fashion. Like suppose you're going to classes, what will you do? You'll put on your clothes, you'll put on your shoes, go down and walk to class. Similarly, this preparation, putting on the shirt and shoes, that's kind of how you define Tmod. That is what defining Tmod is. You're preparing yourself for the classes. So you define Tmod in which mode it has to operate, what timer it has to operate. Then you do the calculation. Please watch the previous timer video to understand all of this better. You do the calculations and you feed the values into TL and TH. CPL P1.5. Why? Because you want a square wave there, right? So you essentially you can define this later on as well. They've done it here. It's up to you. So since you want a square wave at P1.5, you will write the CPL P1.5, start the timer, all of that will happen, and then there's going to be an S jump over there, and then when it comes here again, it'll flip the value. So essentially, P1.5 has some value. It's being held, it's being held, it's being held while the timer is running. You S jumped over there, you came here, this line happened, then you CPL'd it, then it switches. Then all of the rest of the code, the ACall delay, they must have defined a delay function. Yes, they have. So in this case, they have written ACall delay and then they've defined the delay function separately over here. Ideally, you shouldn't really be doing this unless there's a special case which we'll look at later, because what you're doing here is just making your code unnecessarily complicated. Why would you want to do that? Let's look at another example. 5 milliseconds on P2.7. Okay, so again, we've seen such examples in the previous video. Whatever time you have, you divide by 1.085 microseconds if it is a 11.0592 megahertz crystal. Make sure to always check how much is the frequency of the crystal which you're using, because if you don't, you can cause some real major trouble. Whatever value you get after doing this division, you take that value, you do 65536 minus that value. One thing you need to note is that you will have some decimal value, just round it up, and you do the subtraction, you'll get some value. THTL, everybody knows this basic question. So yeah, let's have a look at another code. Yeah, see, this is what I meant. You can actually define the CPL line over here or anywhere later on, but they've just chosen to do it there before. Calculate TL and TH to get the largest time delay possible. Now, this is an interesting question. Now, your crystal frequency is set at, in this question, let's just assume it's 11.0592 megahertz. If my frequency is set to 11.0592 megahertz, usually after I do the division and stuff, I do 65536 minus some value and get another value which I split into two, right? For TH and TL. What if I want the maximum possible delay? In that case, I will do 65536 minus 0, right? So that's what you do, 65536 minus 0. But how do you know exactly what value that represents? Well, you take this value and you multiply it by 1.085 only in the case for 11.0592 megahertz. Once again, this value is only for this crystal. If you have a 22 megahertz crystal, it will be different. We look at some examples later on. And how do we get that value? I've mentioned it in my previous video. I'll mention it once again. So yeah, you do this multiplication and you get the value of around 71 milliseconds. That is the maximum time delay which 8051 with 11.0592 megahertz can create. Now, we will look at some questions later on where suppose you want to generate a time delay of 1 second. My maximum possible delay is 71 milliseconds. So what I will do is I will write a timer code, a block of code, which generates a 71 millisecond time delay. And then what I will do is, see, 1 second is equal to 1000 milliseconds. If I divide this, I'll get approximately, let me just do a quick calculation. You will get around 14. So what I will do is, if I run this block of code, which can generate a time delay of 71 milliseconds 14 times, then I can get a 1 second time delay. So essentially, I can run this block of code how many number of times I want to for how much ever delay I want. That's a very important question for microprocessors, microcontrollers. Comes almost every single year. Now, suppose you have questions where they ask you to generate a square wave of some frequency. Such questions, one thing you have to keep in mind is they have given you frequency. We know that 1 by frequency is equal to time period. The keyword here is time period. When you're writing your code, this is one place where lots of people make the mistake. When you're writing your code, in your TH and TL, you don't define the time period. You do the calculation with the time delay. That is very important to know. So what does time period and time delay mean? See, frequency, suppose I have a 2 kilohertz frequency. What does that mean? That means in 1 second, this thing switches from on to off 2000 times. That is the frequency. 1 by frequency gives me the time period, which is this. How much time it takes for one on and off thing to happen gives me time period. What is time delay? This is time delay. So if they mention time delay, suppose they say 5 milliseconds, then you can directly do 5 divided by 1.085 microseconds, get that value, do 65536 minus that value, get that other value, which you can split into TH and TL. If they mention time period, then what do you do? So then, look, you do T equal to 1 by F. After you do T is equal to 1 by F, you get 500 microsecond is the period. We want delay. So you will divide 500 by 2. So you get 250. Then you do 250 by 1.085 and then you proceed with the normal calculations. So yeah, the code is the same, obviously. This is another very, very important question. So for, the good thing about this question is I can also show you what if you have like a 22 megahertz crystal, stuff like that. So again, it's a very simple, straightforward question, how it normally goes. It's just the same way. So first of all, our crystal frequency is 22 megahertz. So what will we do first? You will first calculate the equivalent of that 1.085 which you normally have. So see, in 22 megahertz, one timer cycle will be 22 divided by 12, which gives you 1.83 megahertz. Then you do 1 by this to get this value. This is your one timer cycle time. If you are confused with what this is, please watch my previous video where I explain how machine cycles work. You will get this in a jiffy. Next, now there is an off time defined here and one on time defined here. So how does that work? Your off time, it's a simple calculation, same way. Normally, what you do, they want some x millisecond time delay. You do x divided by 1.085. You get some value. You do the 65536 steps. Similarly, over here, instead of 1.085, you have 0.546, which you have calculated. Again, make sure to pay attention to what the frequency of the crystal is. And then you do, first for T off, you calculate it. So 10 divided by this value gives you the cycles. 65536 minus cycles gives you the hex value which you want. Similarly, you do the on time calculation. Now, once you do that, you have to pay attention in the code. Normally, your code is not this long. Your code is usually just going to be something which you define the T mod, you do the TL, TH values, and then you write this stuff, the start the timer, the JNB, all of that. Over here, though, we have some time where we want it to be off, right? 10 milliseconds. And we have some time where we want it to be on, 3 milliseconds. So we write the code in accordance to that. So that's why over here, you see, you define T mod, you defined TL value, TH value, and then you defined the output needs to come on P naught. So that's why over here they've written P000H. Why? Because, see, remember this, TL0 has 75, TH0 has B8. So total value is B875. B875 is my hex for the off time value. Off time is B875. That's why over here port 0 has the value 08 and you have defined B875. Similarly, my on time value is EA8A. That's why over here you've defined TH as EA8A and you've defined port 0 as FF. And over here, if you remember, I previously said, right, the A call delay, writing it as a separate thing is not useful unless there's a special case. This is that special case. So in your ORG 0000H, you will write this code, and in another ORG, you will write this code where you write your set bit again, all of that. Why? It just saves you time. Again, otherwise you have to write this block of code over here first and then again over here, which I think is completely unnecessary. You can just write it this way. So yeah, if anybody doesn't get this, you can reach out to me, the mail ID. But yeah, let's continue. So what if they say pulse of 2 seconds, 2 seconds period? Let's keep that in mind. 2 seconds period. What does that mean? If this is your square wave, this duration is 2 seconds. What we actually want is a 1 second delay. So the time delay which they want is 1 second, right? My crystal frequency is 22 megahertz. I'll do the 22 divided by 12, get that value, all of that calculation to get at 0.5, what is that? 0.546 value. Now, the maximum delay which this crystal can offer will be 65536 multiplied by 0.546, which is equal to 35.78 milliseconds. So if I want 1 second long delay, I'll do 1000 milliseconds divided by 35.78, which will give you 28. So I will write a block of code which can generate a time delay of 35.78 milliseconds and run that 28 times to get my 1 second long time delay. So that's what they're doing in this code. So basically it starts off similar, except for this line. So 28, right? We want to run it 28 times. So what we're going to do is you define your T mod, you write the complement. By the way, you have to write this right after the 28, because what you're going to do is this part, you're going to run it 28 times. And how are you going to do it? Which part of the code does that? This part, DJNZ, decrement jump if not 0. So your standard timer, like you load the value 0. Obviously you have to load the value 0 because you want the maximum possible delay, right? You start the timer, you start the JNB stuff, clear TR1, clear TF1. Now decrement jump if not 0. You will take R0. What value does it have? 28. I will decrement it by 1. What do I get? 27. It's not 0, right? If it is not 0, what do? I jump to back. So I'll again run the timer once again. By the way, the first time I ran it, 35 millisecond delay was generated. Now I jumped again 35 millisecond delay is going to be generated. Again, I'll do this, I'll come here, again I'll decrement this by 1. What will I get? 26. It's not 0, again do it once again. I will keep doing this how many times? 28 times. Once the 28th time is complete, I will have generated a time delay of 1 second. And that's when you go from this line to the next line, and then you go all the way start, and then you reload. By then r naught will become 0, right, because you're continuously decrementing 1, and then you continue. Let's see another interesting and important program, if we have any. This is a simple program, you guys can figure it out yourself. Let's have a look at counters. So your timer can also be used as a counter. How exactly does that work? You plug in, well, whatever you want to do, you basically plug in an external pulse. It feeds into one of the ports. If it feeds into a port, that means that port is being used as an input. So once again, refresh your memory about IO ports. You will set that as an input port. So let's just have a look at this text over here. Timers can be used as counters to count events happening outside the 8051. When it's used as a counter, the pulse outside increments the TH and TL values. Programming the timer happens in a similar way. One important thing to know is earlier, if you remember, the T mod register was an 8-bit long register, right? Where you had the C/T, the gate, the M1, M0, and the same thing repeated over here. Oh, in this case, the C/T was what defined it as a counter or a timer, right? This time you're going to be setting it as 1 to use it as a counter. So one thing to know is the counter can only count pulses which you feed in from pins 14 and pins 15. That is port 3.4 and port 3.5, as this is tied up to timer 0 and this is tied up to timer 1. Make sure that, especially in practical exams, you can't just randomly put it off anywhere and then think like, oh, why is it not incrementing? No, it won't work that way. So let's have a look at one of the codes. Oh, by the way, don't get too scared by this. They just, if you see this, they've defined it in binary. That's why it's so long. So yeah, you define your T mod, then T at 0, you clear T at 0 because that's where it's going to start incrementing the values. You set bit P 3.5 because, like I said, you have to make it an input. Then you start the timer. Then what you do is, in this question, they're saying the clock pulses are fed into pin T1, which is P 3.5 from here. And the clock pulses are fed into P1, and you want to display the state of TL1 on P2. You count the pulses and display the state of TL1 on port 2, which connects to 8 LEDs. All right, fine. So yeah, what I'll do is I will get the values in TL. I will store them on A. And then from A, I will move them to port 2. Then I will keep doing it forever. That's why you have your JNB TF1 back. You do it till you don't get any more pulses as input. Jump if no bit TF1. Same timer functioning. You just need to remember that you will have one line over here where you're involving A in this case, and that's it. There's nothing else. Exactly similar to the timer function, nothing different. It's going to be the exact same thing. Do not get confused. If you have any questions, you can, if I'm free, I'm moving to Sweden, by the way. I can sit on a one-on-one session with any of you if you drop a mail or whatever it is. Yeah. Let's look at another question. 22 megahertz is the crystal frequency. Always keep an eye out for this. Configure timer 1, port 3.5, timer 0 as a counter. All right. So receives inputs from P3.4, P3.5. Okay, so let's look at the code. First, you define your T mod as 15H in this case because you're using timer 1 and timer 0. How do you know what value to define T mod as? Why is it coming 15H? This is why you need to learn the structure of the T mod register, because you will have to understand what exactly it is you're doing. Is that 8 boxes? Okay, I gotta erase a tiny bit of it. So yeah, if you guys remember, please check it out once again. You have your gate. I'm not too sure if this is correct. I'm just drawing it from memory. I think it's like this, but have a look at it once and then make sure to remember this diagram. It's very important. So now, how did we get that 15? 1, 5. So 1, which means I'm using timer 1 to generate a clock pulse, right? That's why if timer 1 is going to be used as a timer, my C/T will be 0, and I'm using it in mode 1, so I'm going to just define it as 0, 0, 0, 1. Now I'm using timer 0 as a counter, which means C/T will be 1, and then I will set this as this way. Is that Yeah. So what is this value? 1. This value is 5, 15H. That's how you get 15H. Now, set bit P3.4 to define it as an input. Move TL0, 0 because you're writing the counter program for the timer 0. Similarly, move TH, 0 to set it as a counter. Then you start the timer, which is going to be working as a counter. And then R0, you're moving 28. The reason you're moving 28 is because, let's read the question once again. Okay, because they want a clock pulse for every 1 second. They haven't done the calculation, but in the previous code where we saw where they wanted a 2-second time period, let me show. Yeah, this question, we saw that the value which you get is 28, right? That's what they're doing. See, even in this code, they've moved R0 as 28. They want a 1 second delay. Same thing is what's being done over here. They moved R0 with 28, and they're probably going to write the code for the TH1, run it 28 times. That's what they're doing over here. DJ and Z0 are not, so it's going to stay in this loop forever till, well, not forever, 28 times, and then you get the 1 second time delay, and then you will display final count values in port P1 and P2. Okay, so yeah, you can't write from port to port, right? So what I'll do, I'll write TL0 to A, and then from A to port 1, TH0 to A to port 2, S jump repeat. Where is my repeat line? Over here. So basically, this is also one important thing which I don't think I've mentioned. Whenever you write any of your codes, right, this last statement or the last short jump or something which you mentioned needs to always point to one point in the code where everything begins, so that you can make sure that the code functions continuously and efficiently. You can't just like put it anywhere you want to. No, it doesn't work that way. So yeah, counters, I think that's pretty much it with counters. Serial communication is something we'll have a look at in another video. I'll record videos for serial communication once I get to Sweden and I find some time. But yeah, anyways, good luck for your exams.